My name is Peter Lenz. I am, as I just said, a geospatial analyst at Distillery. I am a member of our data science team. I am loath to actually call myself a data scientist because unlike the other DS members who have, stats and our backgrounds in physics and nanomolecular machines, I took Latin. I studied maps. I didn't learn Python until I was in my 20s, which is really interesting because I end up at a company that's kind of the definition of big data. And clicky, clicky, maybe, yes, wow, that's not what that was supposed to do. Go back. This is why you don't buy a clicker the day before. At Distillery, we're a programmatic ad company. Every time you're seeing an ad on the internet, it's an auction. And there are dozens of companies that in real time are bidding to show an ad to you. And we figure out how much we're going to spend and if we even want to show you ad using machine learning algorithms. And one of the inputs to that is geospatial data. We have every day about 80 billion transactions. A large percentage of those are going to be those bid requests that are auction opportunities. One of the unique things about Distillery is that we license a huge amount of non-ad monetized data. So we're seeing all these advertisements. We're also seeing web pages. We're seeing apps that don't have any ads. And we're seeing a lot of data that we use to build our algorithms. Each one of these bid requests, we have 200 millisecond timeout. And of that, about half of it is actually used up in transit time. So we really only have about 100 milliseconds to apply. I think last time I checked 50,000 or so machine learning models that we can apply for different ad campaigns, audiences. This is all anonymized, by the way. We've actually been called Boy Scouts in the industry because we really do believe in anonymization. Every day we're gathering about 15 terabytes of data, and that flows into our 20 petabyte Hadoop data store. When I was collecting these numbers, which are really, really impressive to me, our sysops people actually told me we used to be the largest Hadoop cluster on the East Coast. We've since been eclipsed by a couple of big banks downtown, but we're certainly one of the largest. And that's spread across 2,500 servers, which I occasionally use to do adding. Hey, why is my clicker not working? You know what? Screw the clicker. So, I want to talk to you guys about practical things. This is the data engineering track. You are the guys who are playing around with the data that we're pulling in. You're making it flow places so that I can analyze it. And in my history playing around with data, I've learned that a lot of the time, you guys treat it just like it's any other type of data. It's an integer, it's a float, it doesn't matter. We play with those all the time. I'm here to tell you that that's not actually the right idea. Spatial data is a special class of data. It is literally real world data. You need to understand what it means, where it came from, how it was collected, before you can have it flow into your data stores. So let's just take one quick example. This is real data that came out of our system about a month ago. These guys right here, I shouldn't have done that, I'm not athletic. That data right there is real lat longs that are flowing to your system where app operators, app developers have transposed latitude and longitude. There's an entire phantom United States down here in Antarctica where the penguins are playing with Snapchat and Pokemon Go. You can just see north of Madagascar, that's the United Kingdom. I've corrected this, rotated it here. You can see how it perfectly lines up. This is just transposing two numbers. And by transposing those two numbers, you had a 10,000 kilometer error in your system. This is, you need to know what geospatial data is. Let's actually get down to brass tacks. The first thing you need to ask yourself is, how was my data collected? You probably think, oh, it's a CSV or it's some kind of stream of data that's coming in. No, we're gonna go back a little bit farther. Like I said, this is real world data. this world. This is the Earth. It's roundish. That roundish is actually a huge, huge issue. You see, when we were kids, we're told the Earth's a sphere. It ain't a sphere. If you went to college, when I did, you learned that it's called an oblate spheroid. If you're one of the cool kids in college now, you learn that's something called a geoid, which means something that's shaped like Earth and is a neat tautology and completely worthless. It's an oblate spheroid. It's a thing that's kind of round. And at a micro scale, that kind of roundness is really easy. We call them mountains and rivers, oceans, the Brooklyn Navy Yard. But there's an even bigger macro scale of non-roundness. You see, and this is going to be a big number. I like this because this is a conference talking about nanoseconds. 4.4 billion years ago, the Earth got hit by another planet. It's about the size of Mars. It's a rogue planet. This is the only photo of a collision of two planets you're going to see at this conference today. And we're part of the galaxy called the stellar crease where stars are born. Our star had just been born there. And when stars are born, they throw off garbage. Not like candy wrappers, planets. It's a rogue planet thrown off by some other star, about the size of Mars, smashes right into the Earth. The Earth is cooling down, but at the instant it hits, it remelts. A shock wave flies through the planet and flings off a whole bunch of debris. For those of you on your computers, you can look up more details. It's called the Great Impact Hypothesis. And this debris will eventually become the moon, believe it or not. But what's important is that it warps the shape of the planet Earth. We're not evenly round. Depending on where you are on Earth, we need lots and lots of different models. Data scientists love models of roundness. So let's take a look at a quick cartoon to illustrate this. This is a cartoon of the Earth. I swear it's not a potato. We have here two datums. A datum is the model of the roundness of the Earth. And the exact definition of that roundness, these dashed lines, we call those reference ellipsoids. You can use that next time you have a triple word score in Scrabble. It doesn't matter which ones they are, but these are NAD 27. We love initializing things in geography. In ED 50. You can see that this dark, bold, dashed line, this is our NAD 27, a datum that you would use in North America. It hews really closely to our cartoon Earth in the area labeled North America. ED 50 skews really closely to the curvature of the fake Earth here in the area labeled Europe. You would never use a European datum in North America. You would get a scale error, a huge error. You would be off by kilometers, perhaps. And there's lots and lots and lots of these datums because the Earth is rounded lots and lots and lots of ways. This is just a screenshot I took out of probably ArcMap. I have a lot of different GIS programs. After a while, they all look alike. You can see some of these are really, really specific. Old Egyptian, old Hawaiian Oahu. In general, as a geographer, you want to use a datum that represents the roundness in as small an area as possible. Back when I was working for engineering companies, including working on this whole Brooklyn Navy Yard project, I would use the New York City's plane, which describes the roundness of the Earth in New York City. And yes, you have to consider this. North is slightly different, the southern part of Manhattan, than it would be at the northern part of Manhattan. You would never think that. It's Manhattan. It's 20 miles long. It matters. If I was pulling in data from Long Island, well, that would be in a completely different datum, the Long Island State Plane. So you're thinking, okay, whatever. These are engineering things. I don't work with this. If you're pulling in any kind of geospatial data, it's in a datum, and you need to know what it is. We're kind of lucky. In our industry, data that we look at is usually at the level of a country or the entire world. If we're working in North America, it's probably going to be in one of those NAD datums. The latest one is called NAD 83 from 1983. At Distillery, we're working with cell phone data. It's almost always in a datum called WGS 84, World Geodetic Standard 1984, which is worldwide. Remember I told you that you try to use as small a datum as possible? Well, that's a datum for the entire world. And quite frankly, it sucks. But it sucks equally across the entire world. It's an equal opportunity offender. And that's really good because if I were to use different kinds of datums, I could get an error like this. So these black lines, these represent ground truth, and that's a term of art in the geography industry. It means the real thing, because anything you collect, it's wrong in some way, it's biased. Ground truth is the real thing on the Earth, our one-to-one model that we can never, ever quite get to. This data was collected in one datum, I don't know, let's say it's WGS 84. And we have a second set of data, which has been collected in, I don't know, it's Manhattan, and it's been collected in Pitcairn Island, which is a tiny little island of Pacific Ocean. We have hundreds of meters of error here, and just real life things. I've seen data companies which pull in data. It's geospatial data. They don't think in the slightest about what datum it's in. It's perfectly good. It's great data. It's really, really accurate. Because they didn't think about what datum it's in, they have automatically created errors in their system that can be kilometers. And it's a really hard bug to actually fix because there's no code error here. It's an error in the way of thinking. It's an error of actually working with the data and understanding it. The error's here, not in our JavaScript. Or if you're working JavaScript with geospatial data, God bless you. So you're probably wondering, okay, how did I actually collect this data? Well, the way you do that is you go out and you collect it manually. You go out there. In the old days, you would go and you'd find some reference point on the Earth. We call it a survey marker. They look like this. You can actually still write to the U.S. Geologic Survey, give them that code there, 53 WSM, and they'll tell you everything about this, when it was collected, what the temperature was, was it cloudy? They'll still have all sorts of different pieces of information about collecting this data. Get back to, that point would be right about here. You see there's a line, there's a brass marker at the bottom of it. This is a known point on Earth. Someone has already collected this information. I'm going to measure the difference between this and some other point. You see there's a chain right here. Your marble notebooks you had in elementary school, they had all sorts of weird measurements. One of them was a chain, a hogshead. That's the chain of the chain in the back of your book. It's actually a measurement that's used in spatial thinking. By the way, the protagonist of this incredibly culturally insensitive painting, that's George Washington. That George Washington, before he was father of his country, rebel general, this is how he actually made his money. He was a geographer. And you're wondering, hey, that was really old stuff. We have all sorts of satellite sensing. That's still the best way to collect that data. Someone goes out there, the only thing that's different is that little machine there has a laser instead of that chain. But you know what? It still measures in chains. Even better, if you just look under here, you can still see a string with a brass weight at the end, which finds this cross in the middle of that point, which is the exact known point. We have never improved on the technology of brass weight on a cotton string to find a known point on the Earth. Just ain't gonna happen. Okay, so you're saying I have a datum, I've collected my data right, I know about it, let's put it on a map. I ask you to think about how you actually create that map. So, in the very beginnings, the early days of geography, we just drew stuff. We just put it down on a map. This is what's called a Portolan chart. It's from the 1300s. All of these little lines, those are actually the names of ports in the Mediterranean Sea. We've got these lines. They're called wind roses. They basically represent the wind comes out of this direction sometimes, and sometimes it comes out of this direction. There's no rhyme or reason to this map. It's just stuff that's drawn. Some of it's to scale. Actually, I take that back. None of this is to scale. It's just kind of stuff. And it didn't matter. If you were sailing from Rome to Cairo, you're only traveling at the speed of the wind and the surf, and you'd adjust along the way. And by the time you make it to the other shore, you're 100 kilometers off. Doesn't matter. I'll make it there next week. It's fine. No problem. But as our world got bigger, we had to start thinking about how to actually draw things that made sense in relation to other things. We started to create what are called projections. A projection is taking that data that was collected in some datum, it's in a three-dimensional space, and putting it down onto a two-dimensional chart. This is about 150 years later, and we've gone from our directions being based on the wind. We have the beginning of a grid system. Things here are more or less in scale to each other. We're getting more professional. Fast forward, a couple hundred years, and we have thousands of projections. This is my toolbox as a geographer. Every single one of these projections has a particular job. I actually do a lot of calculations of figuring out distance in Lambert equal area conic, but it looks weird. It's got this curvature to it. So I actually do the display in Mercator. Maybe I want a particular projection that shows things in scale to one another. Maybe I want one that's good for navigation. There's thousands of projections for thousands of different jobs, and I can't tell you which one to use. In Datums, it's easy. Find the one that's the smallest one. Projections aren't easy. You have to find the one that actually fits your data and fits the story that you're trying to tell. Let's illustrate this. We have here two different projections. On our bottom, we've got good old-fashioned Mercator that you recognize from your elementary history textbook map of the world. On the top, we have Nomic, just a random other projection. We have these two lines in Mercator. We have this nice sweeping great circle route. On a spherical Earth, the shortest distance between 2 points is a circle. It's an arc because the planet's arced. On Nomic, we have this big flat line that goes straight across. In Mercator, we have these points. They're evenly distributed every 5 degrees. These are the exact same line. Those points are the exact same points. That point up there with the arrow, that's the same point as the point down here with an arrow. We're looking at the exact same data, but we're looking at it in a completely different way because we're looking at it with a different projection. We've changed the story, and that's why I can't tell you which ones to use. Your projection, it literally is your view of the world. I'm going to belabor this point. It's really important. 3 different shape files. Actually, the exact same shape file projected 3 different ways. This is the United States, the lower 48 states. We've projected it 3 different ways, with the common point being Omaha, Nebraska. It's centered on Warren Buffett. The three projections you see here are unprojected latitude and longitude. I can't tell you how many times I've seen this mistake made. You take lat long data and you just draw it on the map with like ggplot. Pixel 1732, that's lat long 1732. Don't do that. It's bad. It's totally, you're not respecting your data. You're really skewing it. You see here Mercator, my good old-fashioned Mercator. You can see how Mercator is a little bit wider, a little bit higher up than our unprojected data. We've taken it and we're making all of our latitudes and longitudes artificially at 90-degree angles. It's actually a really good projection for plotting naval travel by ships, which makes sense. That's what it was invented for. And finally, we have here Lambert conformal conic. This is a projection that's trying to, and somewhat succeeding in showing all of these shapes in exactly the same scale as each other. But look how far off they all are. This is the same data, exact same data, very different ways of looking at it. When you're playing with your geodata, you have to think about the way you're actually showing it to your users. Okay, I'm going to go quick because I'm starting to run out of time here. Be skeptical about locations. So, remember these guys? They're coming up with really accurate data. These guys can go down to thousandths of an inch. You ain't getting that data. You're getting much worse data, which is coming out of this thing called the Global Positioning System. And GPS isn't just GPS. There's also the Russian GLONASS system and the European Space Agency's Galileo. China's building a system. India's building a system. There's a plethora of these things. The skies are crowded. And a GPS satellite is this thing. It is a power system, a battery, an antenna, all of which service these things. This is a cesium atomic clock. And there's going to be 2 of these in a GPS satellite. There's also going to be 2 rubidium atomic clocks in there. And what is in there, there's a gaseous form of cesium. There's a laser. That laser is shooting through the cesium. That cesium is getting excited and it's vibrating at a really, really constant rate. And that it can easily be measured. And it's really, really accurate. We can get down to millionths of a second. And reason we have 4 is that as accurate as those are, they have to be launched into space on top of an 18-story, 400-ton pile of explodey, which makes them slightly less accurate. So 4 atomic clocks, you have a complicated weighted average of those times. Those times are being broadcast out by the antennas on these GPS satellites. And your cell phone, your GPS receiver, it's listening for them. And through a process called I never pronounced this right, translateration, not triangulation. Triangulation is in a 2D space. This is existing in a 4D space, X, Y, Z in time. We can actually compare spheres. And where those spheres overlap, that's where you are. You need a minimum of 4 GPS satellites, but you want as many as possible. A quick digression. When I used to work for the National Park Service, we actually had a program that would tell us when there would be as many GPS satellites overhead that we could connect to at a particular time to record as accurate information as we could get. So if that meant that you had to be out 12 miles from the nearest road at 3 a.m. on a Sunday, you got your ass out 12 miles from the nearest road at 3 a.m. on a Sunday to collect that data. So that's how GPS works. Now I'm going to tell you a secret. Your phone never uses GPS. GPS, it depends on you standing still. When I was out there at 3 a.m., I would have my GPS receiver set up for hours so that it would get accurized. You don't have that when you're trying to figure out how to get from York Street Station over to the Brooklyn Navy Yard. Your phone figured out where you are pretty much instantly. It cheated. It actually was talking to the cell phone towers using a system called AGPS. AGPS has a GPS receiver on a cell phone tower. That receiver, it's survey grade. It's not the crap that's in your phone. It's gigantic. It has a dish that's feet across. It's not moving. It's literally bolted into the concrete. It knows where it is with incredible accuracy, and it's broadcasting out a signal that your cell phone is looking at. Your cell phone can cheat in other ways. If you're going faster than a certain speed, it's going to snap you to the nearest road. You think that looks accurate. No, it could move you tens of meters. It could move you hundreds of meters, which creates a big problem for us at Distillery. All we get is latitude and longitude. We have no quality measures. We have no error bars. We just get lat and long. So we have to build our own classifiers to actually take just lat and long and figure out how accurate it is. We have 4 levels of geodata. There's wrong. You saw that at the very beginning with my transposed latitude and longitude. Let's just forget about that. And numerous other ways you can screw that up. I have stories. Let's focus on the good stuff. There's hyperlocal. Hyperlocal data is good within a couple of meters. This is your phone really actually connecting to the GPS network. And you're sitting still for a very long time. I can use this to generate insights on, like, for instance, a specific store, a big box store or something. We have mesolocal, which cleverly just means in the middle. Mesolocal data is, I can't put you in a building, but I can put you in a zip code or a census tract. It's something that's, a couple of kilometers inside. There's broad data. Broad data, that's usually centroids. You're in the centroid of New York City, which is in a Duane Reade just north of City Hall, by the way. I've been there. I'm insane. I'm a geographer. What do you want? You might be in the centroid of New York State, maybe the centroid of the United States or the world. So we have all this different data. We've collected it. Remember, we have 80 billion pieces of lat long every day. I can be picky about throwing it out. In fact, we throw out 2/3 of all the data we collect. We are generating insights on this stuff. If we use crappy data to generate it, we generate crappy insights, and nobody wants to pay for that. So we use a couple of filters to clean up our data. The first one is the manhole cover. And the manhole cover is best illustrated by this fine Catalonian tradition. When you get data, and just lat longs coming in, they look really accurate. They've got a lot of decimal points. And those decimal points, they correspond to really accurate locations on the Earth, feet or inches. Well, the manhole cover counts. That's all it does. We're working with 80 billion things a day. It can't be that complicated. So we count how many people are at this exact lat long for a particular time period. And if it's more than, say, 5, and we experimentally move that up and down over time, 5 as n, we say this point is not hyperlocal. This isn't good data. This is not stuff that we want to be building out good information on. This is the most metropolitan place in the United States of America. This box right here, at any one time, there are thousands of people standing on their shoulders at that exact point. This is the geographic centroid of the lower 48 states. And it's in the middle of nowhere. And our system, if you look at the manhole cover, thousands of people here. You're not there. Your system, your phone, for whatever reason, is saying, I'm in America. That's all you get. It could be because you have privacy settings. It could be because your battery's going low and your phone is cheating and doesn't want to actually figure out where you are. It could be because, remember, we're a programmatic advertising company. Ads that have location data attached to them are considered more valuable than ads that don't have any information attached to them. Your app developer has an incentive to send us crap. Sorry, excuse my language. It's what it is. Oh, by the way, great story here. The people who live over here kept getting visited by people who are looking for their Macs or for their iPhones because they were located to this point. They actually sued and had the geographic centroid of the United States moved a couple of kilometers that way in the middle of a lake to prevent people from showing up there. Totally true. I've been intending, by the way, to just drive past here just to visit. Anyway, the busiest place on planet Earth is right here. We call it Knoll Island in the geography world. By the way, I just remembered I had a laser pointer. And Knoll Island, according to our system, there are tens of thousands of people there at any particular moment. This is what Knoll, and that's why I wasn't using this thing, Island looks like. It's actually this. It's a pirata buoy. They actually use it for predicting hurricanes. Hiding behind where it says Atlas is about 100,000 people at any particular second. So this whole set network of geos, this is one particular app. This is organic data that we're getting in. It looks really, really good, right? Maybe it is, but this is what the manhole covers look like hidden in that data. You can see they make a pattern across the Earth. We call this the grid because we're really clever about naming things. They're in a very, very regular pattern. We've used Fourier transforms on this data to be able to find all the other points in the grid. We know every point on the grid on the planet Earth, and we know that if you show up in one of those places, you're not actually there. It might be inside of a Walmart, you're not in that Walmart. You're kilometers away from it. Don't use this for good insights. The last filter, well, not the last filter, but the last one I'm allowed to talk about is my favorite. We call it the Superman filter. This is real data. This is the most egregious example I could find in our data. This is one device traveling across the period of a day. So the Superman filter, it's a very simple rule. If you break the speed of sound between two observations, you are not actually real. It's super simple. And you would be amazed how many bad actors it catches. You don't need to have really complicated, sophisticated filtering. These three filters kick out 2/3 of all the data, of the 80 billion points we're collecting, to get us to good data. I'm going to finish up really fast because I only have a few moments. Use the right tool for the job. Once we've collected this data, we've treated it right with the datums, we've projected it right, we actually have to generate insights from it. So when I started at Distillery, we only had one system, and it was called Uncle Jesse. Not that Uncle Jesse. That Uncle Jesse. We're called Distillery. He was a moonshiner. I didn't name it. It's not my fault. Uncle Jesse is a PR tree. You've been waiting for me to actually get to data structures, haven't you? It's a PR tree. And a PR tree, a priority R tree, is basically a spatially aware tree. The items to one side of, to the left side of this data structure are to the west. the atoms to the right side are to the east. Every step of this tree we prioritize. We basically figure out what are the closest points using KNN, and we say these are the ones that are the childs of these the children of this level of the tree, and we keep walking down. It's really fast. We have millions and millions of points of interest inside this database, and we get single-digit millisecond return times. And the reason we do that is that it lives in memory. You can see where the problem is. We have lots and lots of places that we're interested in because we evolved from just a programmatic company into a company that also does insights. That meant that this was getting really, really big. We only have so much space that we can put on our machines that we can look at them live. So we had to sit down and say, how do we actually do both fast lookups and really, really good insights? And the answer was we built a second GIS. I know that that violates computer thought, that you build one system and you keep using it. But by using two different systems, we actually got real flexibility in speed. Our second system, I keep forgetting that doesn't work. Good job, Staples, is called Geo Tiles. And Geo Tiles is a tessellating grid of 100 meter by 100 meter boxes that spread across the entire Earth. Every box has a unique identifier. And the algorithm that we use to generate those identifiers, they're reversible. I can take a lat long, convert it directly into an identifier. In fact, that's the last thing that Uncle Jesse does before it passes off to other parts of our programming. It generates this ID. I can take that ID and turn it back into a lat long. And it anonymizes your location. I don't know exactly where you are in this. This is a cartoon, by the way. This isn't real data. And this would be a cartoon of a census tract in Greenpoint, Brooklyn. So here's a grid point. That point is mapped to this polygon, this census tract, but it can be mapped to almost anything. It also belongs to a polygon that is the zip code in this area. It's mapped to a polygon that is Brooklyn. It's mapped to a polygon that is the city of New York. It's mapped to the polygon of New York State. I can map it to any kind of insight generating thing I want. Think of it this way. It belongs to the Crown Lands. It belongs to the King's Landing DMA. I was given a bet that if I would use this or not. It belongs to the Castle Geo. We have two systems. One collects things really fast. One lets us go in after the fact, after data is in our data store with this Geo Tiles ID and generate lots and lots of data from it. So, six tips. Spatial data is different. It's special. You have to know about it. You have to know about how it was collected. What datum was it in? How was it? What scale was the data? You have to think about how to visualize it, how it's going to be projected, and what the different uses of all those different projections are. Hint, hire a geographer. You have to be skeptical about your location data because your GPS or whatever you're using, it's lying to you in very subtle ways. You can be picky. When you have lots and lots of data, it's okay to throw out lots and lots of data to just find the best stuff and use the right tool for the job. It's okay to build multiple systems that do similar jobs or even the same job so that you can optimize for speed and lookup. My name is Peter Lenz. I have a broken clicker. I am a senior geospatial analyst at Distillate. I'm over my time, but I am very interested in any questions you guys have. Thank you.
Yeah, what causes the Superman effect of the devices flying around the Earth?
So there's two things going on there. First one is just plain fraud. Remember how I said that that advertisements, the bid requests that have location data are more valuable? People lie about the exact location. Maybe you're in Hollywood, Florida, but they say that you're in Hollywood, California, because a person who would be located there presumably would be in some kind of luxury segment, be worth more money. The other thing is just your GPS going nuts. GPS can cache location data. The number of times that you see things like someone getting on a plane in New York and it's still sending out that location when you get off a plane in Los Angeles, you'll see a lot of that stuff. And then, of course, there's just junk. There's a lot of junky data out there.
What about continental drift? How does that affect your calculations?
It actually does, believe it or not. For instance, the Adirondack Mountain is just a couple hundred miles from us. That is actually growing at a rate of about a centimeter a year in height, and that's glacial rebound. That's actually not like continental drift. That's the Earth is still bouncing back from the end of the weight of the ice sheet from the last ice age 10,000 years ago. We're still recovering from that. That's the great thing about geography. It's way bigger than any of us. No matter what you think you are, how important you are, geography is bigger, and it's got bigger things and bigger numbers. It's cool, sexy. And to give you a serious answer, we have to actually update our datums every couple of decades because things are moving around. Leap seconds, which you also hear about, that's the same thing for the GPS system. We're actually correcting every time there's a major earthquake, the Earth actually slows its rotation slightly. People don't think about this, but the Fukushima earthquake actually made us do a leap second a couple years ago. That affected all of my systems and made them less accurate until we were able to update for it. Yes, we have to think about that.
Do you have a process for figuring out whether or not you're throwing out too much data?
So that is the art side of data science. There's no ground truth about what good data is. The proof is kind of in the pudding. We generate insights and we share them with our clients. And independently, they have systems that are generating very similar insights. The fact that we have two separate systems that are generating a lot of the same data, that suggests that we're getting a good amount of data. There just isn't some formula that I can say this is the exact amount of data I should be throwing out. I can look into it and say this doesn't pass the smell test. This looks funny. This is a grid. Why do we have this? It's the art side of data science, and there's no way to quantify it.
If the phones are using Wi-Fi to detect where people are right now, and how accurate do you consider this GPS information based on the Wi-Fi network?
So yes, phones actually have a hierarchy of different systems that they use to locate yourself. GPS is at the bottom of it because it uses a lot of power to listen to those GPS satellites, which have weak signals sitting up there 20,000 kilometers above us. A GPS uses power, and then you can look at SSIDs. And this is Google Street View is driving around. It's taking pictures. It's also snarfing up Wi-Fi names. And when you connect to Google Maps, or Apple does the same thing, and lots of other companies do the same thing, they're actually passing on the SSIDs of the Wi-Fi networks that you are near, and they are saying, where in our database did we see these unique names? This is your location. It's a cheating way. I never even have to go and look at any kind of spatial information. I don't have to look at GPS or anything. It can be good in a place like a city. It depends entirely on how old the data is. You know, there's places where Street View hasn't been in 5 years. It's going to be really bad. In a place that's a city like this where they go all the time, it can be good. We don't actually know when we're getting that data. We have no idea what the source is. I would love to do that experiment and find out. I can't.
Yeah, funny story actually. I was in a hotel in Valencia, and because it was a Holiday Inn, it mapped me to another hotel in Malaga, which has the same Wi-Fi name.
Yep, that happens all the time. I used to work for the National Park Service. We had a Wi-Fi name. They're specified by government IT people, and they're the same in every single park. It would regularly locate me in Fort Collins, Colorado. I worked in Yosemite, in California, in the Sierras, but they would put me in Colorado. I cannot tell you the number of times I saw an ad for this particular Coloradan tile company who were trying to get me to visit because I was a local customer. Not really. Yeah, that's totally a thing. I would love to do that experiment.
Okay, last question.
What kind of databases do you guys use at Distillate to process?
So most of our data is in Hadoop. We actually have a gigantic Hadoop cluster. That's most of that 20 petabytes. We also have online live geospatial things that we're running. Those live in Postgres that we use for display. None of our backend is actually in that. Only display is in Postgres. Our backend systems are either that PR tree I showed, the Geo Tiles system, which is just an ID basically, that is a key key value store, Cassandra, or it goes into Hive. We love Hive. We were actually one of the first users of Hive, and I love it.
Okay, great. Thank you very much.